is Lia Bronsard from McMaster University, and this is the first of 3 lectures by Professor Bronsard, and it's about vortices in Ginsberg-Landau systems.
Thank you very much. I would like to thank the organizer for inviting me to give a mini course. This is my first time giving a mini course anywhere in Brazil in particular. I'm very proud also to be part of a school which has such a beautiful poster. I feel very important. It's also very nice to be in Brazil. Back home we have the same temperature at night, 23, but in Fahrenheit rather than Celsius. Okay, so this is a mini course. So I'm starting on transparency just so that we can have an idea of the type of models for which this framework works. But after we go through the introduction, I'm going to switch to the board because this is a mini course, so I'm going to write on the board, hopefully. You can see well. So feel free to come forward if you don't see so well once I switch to the board. Okay, so I'm starting with the general framework. So what are Ginsberg-Landau model? They arise from Landau's general theory of phase transition, in which you describe a physical state by an order parameter or wave function. So more specifically, I'm starting with a domain bounded in Rn. I will take n equal 2 all through this talk. And the general Ginsberg-Landau energy is written as this. So you have this Dirichlet energy, and you have a potential W. I'm assuming psi is in this nice subwave space, and normally it's complex valued. Oops. And so the potential we assume is non-negative and vanishes on some manifold. No? So the problem we're looking at are really trying to find minima or critical point of this energy functional, this Ginsberg-Landau type functional. And written this way, it's going to be subject to some boundary condition or appropriate constraint. And I'm just making the observation that critical points solve an Euler-Lagrange equation, which is written just down there, which is a system. You have to realize we're dealing with psi, which is in general, complex valued. So we have a system of nonlinear partial differential equations that is behind these critical points. And what are we interested in studying? So I did not mention, but there is a small parameter in the energy. We're going to consider what happens as epsilon tends to 0, which comes from application looking at large, high-temperature superconductors. So what happens as epsilon tends to 0? So assuming that we have some sort of convergence, which otherwise would be sad here. So assuming that we have some limit, let's call it psi star, notice that because of this 1 over epsilon squared in front of the potential, and the potential is non-negative, this will force, as epsilon tends to 0, the minimizer psi epsilon, the limit of the minimizer to basically converge to the manifold on which W is vanishing. Which means that we're going to have in the limit this sigma is my manifold on which W vanishes, a sigma-valued map, which must at the same time minimize Dirichlet energy. So we end up in the limit to a harmonic map, which is valued in the manifold where the potential vanishes. Now, asking for psi star to be sigma-valued, if the topology of this manifold is a bit interesting, it may not be possible for psi star to be taking values in this topological non-trivial potential. And so what happens in the limit is that there's some singularity which are formed. And these singularities is what we are really interested in, both in math and in application. And we want to understand the type of singularity, where are they located, how many will there be. And actually in this mini course, more importantly, we're going to concentrate on what is the structure of the minimizer near these limiting singularities. So let's look at the basic, simplest example here. So omega, again, is a bounded smooth domain, and U is complex valued. And this is the potential is simply mod U squared minus 1 squared. That's the potential I'm considering, which the manifold in which it vanishes is S1, the unit sphere. This has real application in superconductivity, superfluidity, and Bose-Einstein condensation. I'm going to present a little bit more of these models shortly. But of course, in this application, you would have something more complicated. I'm calling this basic. You would normally have some coupling with either magnetic potential or with a rotational vector field if it's a superfluidity or Bose-Einstein condensation. But what we understand in this basic model actually help a lot. It's amazing how a nice model can help even in very complicated systems. So since we don't have this magnetic potential or magnetic field, what we're going to do in order to get these vortices, this singularity to form, we're going to impose Dirichlet boundary condition. So we ask that on the boundary, U be equal to G, where G is S1 value, takes values on this manifold. In which case, repeating what I said before, we expect minimizer for this basic example to converge to a limit which will take value in S1. So the modulus of U star is 1, so you can rewrite it as e to the I phi star. So we have a phase associated to the limit of the minimizer. And so again, we kind of see what's important. We kind of see the degree here. So if you have a finite energy in the limit, so U star is H1, this is the only possibility is that the winding number be 0 due to the smoothness of the minimizer. But if you're imposing on the boundary degree, which is non-zero, then you're forced, the degree of U star cannot be 0, and that forces U star to have singularity. You cannot both be S1 valued and be regular, so U star must have singularities, which is what we're studying, the vortices. But I will be concentrating more on this two-component Ginsberg-Landau model. So let me present what I'll be concentrating on. We have now a two-component order parameter. So now psi is C2 valued. And the energy is, so it starts as usual with the Dirichlet problem. Now this is the potential. So psi squared minus 1 squared, but also here this term, the first component squared minus the second component squared. This, notice, so this constant beta here is positive. It's going to be important. We're going to see it has some effect on basically the shape of the vortices. And this term really corresponds in physics to a spin, actually. So when beta is positive, what we're asking is for the spin to be penalized. And this spin, this application is in superconductors or Bose-Einstein condensate, which we have to take into account in addition some, in fact, ferromagnetic effect of the superconductor. So there is some spin interaction. And that's why we get this two-component model. So let's look where is the potential vanishing, because that's where in the limit, where the limiting minimizer must live in this, where the potential vanishes. So you see again that you want to have mod psi squared equal to 1, but in addition you want psi plus to be equal to, in the modulus, to be equal to psi minus. So what we see is that the potential vanishes on basically two torus. Both psi plus squared and psi minus squared modulus must be equal to 1. And so these two torus you can actually parameterize by two real phases. So now we're going to have, instead of just one phase and studying the winding number, we're going to have two phases, and we're going to have hopefully new type of topological vortices. So that's what I just said, a sigma valued map. We carry 2 degrees around any closed curve. Each component will have a degree associated to it. So I just say a little bit that this is coming really from the physical motivation. This potential is really rewriting, we make a change of variable, it's coming from this physical system where we really see the spin here in the potential. And it's a question you just rewrite, make a nice change of variable to convert the problem I just said earlier to this physical system in which we really see the spin enter in the model. And what is nice of this, when we write it in the spin interferomagnetic, if you want, superconductor model, actually, if you rewrite the sigma value, the psi tilde, so I'm writing psi tilde as psi1, psi2, psi1, psi2, so you have an overview, a preview of how I'm writing. Hopefully you can read this. The point is that the potential, the manifold in which the potential vanishes can be written as e to the I theta cosine omega and e to the I theta sine omega. So this will make mod psi square, psi tilde square equal 1 and the spin psi1 cross psi2 equal to 0. So what we see here is that we have 2 degrees associated again to the psi tilde, to a sigma valued psi tilde. And what we see is that the minimal period here, we don't need to turn by 2 pi the angle. We just need theta and omega to turn by pi. So we end up with some half degree integer, some fractional degree integer, with still the property that the sum must be nz. So these fractional degree vortices corresponds to, once you make the change of variable, to the vortices we're going to study. And now I want to present just a few more models where this method, this general framework applies. First, actually, the 2-component model I told you is, in fact, even a simpler case. It really, you can think of it as a toy model for the 2-component Bose-Einstein condensate. So I wrote here the most general potential for this with some appropriate control on B and A plus and A minus. Because we're looking at Bose-Einstein condensate, we actually have some confinement, so we have some mass constraint, which allows us actually to see the potential as we complete the square using this mass constraint. And we end up with a potential here, non-negative, which, again, will vanish on a slightly more complicated manifold than before. But so I'm going to speak a little bit from time to time what happens when you have a slightly more complicated 2-component. There's even more interesting, different topological type vortices, even more than in the simplest. And the simplest case I presented is when A plus and A minus are equal. And I'm calling B1 minus beta. Then you reduce this to the simpler 2-component. And as I said, some recent extension to this more complicated 2-component Bose-Einstein has been studied recently by San Alama and Shigao. So now really slightly different Ginsberg-Landau system, one in which, again, similar idea applies, is the Gross-Pitaevsky system, written here, where gamma is bigger than or equal to 1. So in this case, you actually have some repulsive, strong repulsion here because gamma is bigger than 1. So the minimal manifold corresponds, in this case, you kind of have a separation of phase. You want either psi2 to be 0 or psi1 to be 0. So you more like it is actually closer to kind of a vector-valued Allen-Kahn model in the modulus of psi1 and psi2. And with recent work with Stan Alama, Andres Contreras, and Dimitri Pelinovsky, we actually study the formation of domain walls which are separating the two phases. And also show gamma convergence to a geometric partition prime expected in this type of transition problems. So this couple Gross-Pitaevskis, again, relates to Bose-Einstein condensate with a strong repulsive interaction in this case. So also Landau-de Gennes model, you can kind of put it in this general framework. In this case, you are describing the state by a Q tensor, which is a symmetric traceless 3x3 matrix. And the energy, again, so it's in this form here where the potential is given in this complicated form here. And in this case, the minimal manifold consists of uniaxial tensors, and which can be equivalent, which is equivalent to the projective sphere. So it's a little bit different now. The orientation is not so important. So there is some result by Bars, Arnescu, Majumbar, Lamy, and also recently with Sanalama and Bernardo Galbao Sousa, where we study these problem here, which we'll see in this case, again, fractional degree vortices. Do you have a question?
Yeah, I just want to is psi usually the potential of the magnetic field, or where's the actual magnetic field?
So,
not only this model, but all the different models.
Yes. So in general, you have to add the coupling, and the coupling with the magnetic potential will be through the gradient term, which will be actually a covariant derivative, and there will be a potential term including the magnetic potential. So you really have the magnetic potential in the gradient term, and you have, in addition, basically L2 norm of the magnetic field. So they have basically an energy which depends on two unknown, right? The order parameter and the magnetic potential. So psi is the order parameter. Psi is the order parameter. Magnetic potential enters into in the potential and in the gradient term as well. Yeah. I don't speak much of the application with the magnetic field because I'm concentrating on the two-component Ginsberg-Landau. So back to what we're going to concentrate our mini course on. It's I call it our preferred Ginsberg-Landau system. So I'm rewriting so we have a two-component C2 valued order parameter, and this is the potential. So we don't have magnetic field, so the way to indeed induce these vortices will be to impose a Dirichlet boundary condition. So I'm going to fix a boundary data here, whose component I call G plus G minus. They are, again, sigma valued, and in this case it's just a torus, whose modulus of C plus is 1 over root 2 and the modulus of C minus also. And I want to have some non-trivial windings, so I'm going to impose that the degree of G don't be that both components not be 0. So I want to consider Dirichlet problem and look at minimizer of this in this setup. And the question is, really I want to study the vortices, given that I'm looking at a two-component system. Are there some really new type of topological vortices in this setting? So I think that this finishes my presentation on, and I had one more. So I do admit that the Dirichlet boundary condition is not really physically appropriate. Really what we should have is an applied magnetic field or some rotation, which will actually make the vortex have some benefits in the energy to appear. Here we are forcing them by this Dirichlet boundary condition. However, we are interested in this mini course at the vortex structure, so what's happening nearby the vortex, not so much at where they are located and when are they, for which applied field are they appearing. And so if we're interested really in concentrating on what do they look like, then this Dirichlet boundary condition is quite appropriate. Okay, so I will keep, I think, this system there. And so I would like to start my mini course on well, what can we say about these vortices for minimizers? So the first thing I will look at really is what is the cost of a vortex? So that would be my first. And I'm going to work on I'm leaving this big one there, but I'm going to work on the simpler, I'm calling it simpler. It is simpler, but I'm going to work on really the first problem I mentioned, the simplest problem I mentioned, where basically beta is 0, okay, which was studied really the starting work on Ginsberg, mathematically on Ginsberg-Landau, is in this very important seminal work of Vortices, Bétuel, and Hélin. In which case, so as I said, this is going to be a much simpler case. I mean, just one component. So I'm going to have psi, in fact, just to distinguish, I'll have psi, which is from a bounded domain in R2, but just complex valued. And again, I'm going to look at Dirichlet boundary condition. So psi epsilon on the boundary is equal to this function g, which is a nice smooth function, sigma valued. So in this case, it's S1, because the potential I want to look at is just mod psi square minus 1 square. Okay, so I'm looking at this energy, but the simpler case. And I would like to know in this simpler, in this S1 valued, I would like to know what is the cost of a vortex. Okay, and I will call this energy, I will simplify this all the time, calling it BBH all the time. Okay, for Bétuel, Bose-Einstein. So what is the cost of a vortex? I would like first to study. And I'm going to give first some heuristics. So as I presented already, we expect the modulus, because this is as the manifold in which F vanishes is mod psi equal 1. We expect here the modulus of psi epsilon to converge to 1 as epsilon tends to 0. This would be, of course, away from vortices. Away from vortices. So what I'm going to do to calculate the cost of a vortex, I'll take some vortex, and I'm going to consider an annulus around this vortex here. So I'm going to be away at order epsilon and choose to go an annulus which is at a distance away from the next vortex. Okay, so I consider an annulus. And we'll call it A of epsilon and R here. And I'm choosing R. And I'm going to assume that's the idea, so an annulus around the vortex. A vortex P. And I'm going to assume that in this annulus, the limit psi star is indeed equal to 1. Because I'm away now from the vortex, I'm assuming the limit, I'm indeed S1 valued in this annulus, away from the vortex. And so therefore I can rewrite psi star as e to the I phi star. And since, again, we have this condition, we have psi star is equal to 1 in an annulus, we have a well-defined degree. You kind of see it. Right, so we have a well-defined degree. Well-defined degree, since mod psi star is equal to 1 in this annulus. And so the degree around any closed contour in this annulus here is simply the integral over the contour of the gradient of the phase, the tau ds. Right, and this represent the winding number of the phase will be an integer. Right, so this is the winding. Okay, so I want, again, to find what is the cost of a vortex. And remember, the energy have a grad c squared. Yes?
Can I clarify the computation, please?
Yes?
Psi epsilon is any of the solutions for epsilon fixed. So it would be more than one solution, correct?
So I'm considering a minimizing sequence psi epsilon.
So it would be like for every fixed epsilon, it would be more than one solution. So it was sequence.
I'm just considering a minimizing sequence. Just a minimum.
Now the next thing is basically you say psi star is equal to 1 in the annulus, but the absolute annulus depends on epsilon. Do you take certain...
So this is again, I'm trying to get some heuristic. I just want to get some idea of what the cost of a vortex is. So this is going to be, you take it with, how to say this, with a grain of salt. Right? I'm just trying to get some feeling for what the cost should be. Okay, indeed, to prove all this rigorously is the whole ballgame.
Just trying to clarify the definition. Psi star independent of epsilon.
Psi-
It says the annulus is basically fixed, but then it's changing in epsilon.
Yes. So I'm kind of approximating, if you want, psi epsilon. I'm kind of thinking of it, since the limit is 1, I'm thinking of psi epsilon here as being close to 1 and therefore having a phase as well. So, and I'm looking at, just trying to get some feeling for what to expect, knowing that in the limit we have this information, what can we get for epsilon small? So, as I said, whoops, doesn't matter, we don't need it anymore. But there's the Dirichlet energy in the energy. We have the gradient term. Can we turn this off? Because it's kind of annoying. I mean, at some point, it doesn't have to be now, but right. So since we have this condition here, psi star is e to the I phi star, we have that the gradient of psi star, if you want, I'm trying to estimate the Dirichlet energy. So the gradient squared in my annulus, right, the gradient of psi star, thank you, is going to be the same as the gradient of phi star squared in the annulus. Okay? And now using my definition of degree, which is just here, I'll be able to relate this to this term. So using the definition of degree, we have that if I square this thing here and multiply by 2 pi, you get 4 pi d squared. So I'm putting the 2 pi here, squaring. It is the integral of grad phi star, the tau, ds squared, right? And I'm going to use Cauchy-Schwarz on this. So ds is just, and where am I doing this? I'm doing this on a circle of radius r around p. So I take a fixed circle of radius r around p. So this is my arc length is r d theta. And now using Cauchy-Schwarz, I get that this is less than the integral of grad phi star squared times r d theta. And here I'm parametrizing here from 0 to 2 pi times the integral of just modulus of tau, which is 1 r d theta. Right, just doing Cauchy-Schwarz. And so therefore now I'm going, this is what? This is 2 pi r. So I'm going to divide this on the left-hand side. and integrate. So if I integrate from epsilon to r, the integral from 0 to 2 pi, and I need a 1/2 grad phi star squared. Right, so I'm integrating here in r. It's going to be bigger than or equal to. I have the 4 pi d squared over 2 pi r. So I'm going to be left with pi, the 4, oops. I says in my class, you're supposed not to let me make mistake like this. So it should be 4 pi squared, right? It was 2 pi. I put on this side. When I divide by 2 pi r, I'll get here, and there's a 1/2. I'll get pi d squared, and divided by r, and I'm integrating from epsilon up to r, dr. Right? And so we get the cost of a vortex, at least heuristically, the cost of the vortex, which is pi d squared, and here we get the log of r over epsilon. So we see the cost of a vortex is fairly big, right? And on the left-hand side, this is what I wanted. Right, when I integrate this, this is precisely the integral over the annulus of grad psi star squared dx. It's exactly this. Okay, so this is the contribution in the energy of a vortex located at P. Notice that to get equality, I have inequalities. We have equality if we choose phi star specifically to be d times theta plus a constant. We get exactly equality. So right, so note. We have equality. We have equality if phi star is d theta plus, you could have some constant alpha, since in that case the gradient of phi star squared is d squared times the gradient of theta squared, which is exactly the gradient of theta squared is d squared over r squared. So we get exactly equality. If the phase looks like this, so if the phase near a vortex looks like a polar angle, okay? And for a minimizer, what do we expect? To minimize this, we would like d to be 1. I'm assuming, by the way, on the boundary I've imposed positive boundaries. We would like d to be 1 for a minimizer. And you also get from this that to highest order, we get an energy for the minimizer psi epsilon to be to leading order. It will be, so there's, if I'm assuming I have a degree d on the boundary, I'll have d vortex of degree 1, so the energy, as I wrote there, will be pi d log 1 over epsilon, the order. Sorry. Okay, that's what we expect for the cost of a vortex. And so, in fact, and we expect again, not only that, but this also suggests that the psi star near a vortex, so in the limit it should look like polar angle plus potentially a constant. Okay? So this is nearby a vortex. You have some vortex, and we expect the phase to look like basically polar angle. Okay? So this was done in rigorous and technical detail by Becher, Brezis, Ella. So they did calculate explicitly, they wanted to calculate this energy, find basically an expansion. What does the energy look like here? To calculate the energy of a minimizer. And because of this heuristic, they realized that instead of working, we expect the phase to look like the polar angle. So we have lots of vortices. We're going to have a combination of these polar phase. They thought instead of working with a multi-valued phase phi star, let's go back to our complex analysis here and associate instead to the phase, let's associate to it the harmonic conjugate, which will be in fact a log. So this was the idea in order to get explicitly the expansion of the energy. So let's recall that the integral of grad psi star squared is the integral of grad phi star squared. And so we were minimizing this over psi star equal 1, which is the same thing as minimizing this, but without a constraint. So phi star is going to be a harmonic map. The harmonic function. So the harmonic function phi star, we just saw is a superposition, is going to be a superposition. Okay, it's a superposition. Superposition of polar angle near each of the vortex. Near the vortex. So it is very nice to have a harmonic function, but phi star is going to be multi-valued. So instead of working with this multi-valued function, they thought, let's look at the simpler function, which is the harmonic conjugate. So it is easier to study the harmonic conjugate. Let's call it capital phi. Harmonic conjugate to phi star, which is, as usual, defined by solving which is defined by solving this equation. Okay? Okay, so it's again the idea of associated to the angle, the log. Okay, the harmonic conjugate, which is the log. So in fact, you expect the harmonic conjugate to behave. Expect the harmonic conjugate to behave like the log near a vortex again. Near a vortex Pj. And so they are able to obtain the energy expansion in terms of Green's function around each of these vortices. Okay, so the BBH, we're able to compute the energy. Compute the energy as a sum of Green's function with poles at the vortex. So again, the idea behind all this is that the L2 norm of the gradient phi squared, which is what enters in the energy, is going to be the same as the L2 norm of the gradient perp of phi star, which is the harmonic conjugate. That's how these Green's function come in. since the integral of grad phi squared is the same as the integral of grad. So this is phi. We can calculate the energy, and BBH have obtained the following result for the energy. So to leading order, we do get what we expected. Again, I'm imposing on the boundary the degree D. I'm imposing to leading order. And now define, using again this Green's function, a renormalized energy, which is giving the interaction between all these vortices. So I should have D vortex, since I'm imposing D. This is called the renormalized energy. Okay, and it measures the interaction. There's going to be also a contribution from the core, the little ball radius epsilon near the vortex. There's going to be some constant. So this is really the energy of the core. Contribution of the energy in a ball radius epsilon near the vortex. And so in the limit, when epsilon tends to 0, you get this, how the energy behaves for small epsilon. So in particular, we find that the vortex location is going to be obtained by minimizing this renormalized energy. Okay? So that gives us at least a part of the answer. We now know by minimizing the renormalized energy where should be located the vortex. But again, I'm going to concentrate more on what do these vortex look like. Let me just make a remark that there are results of Gerard Sohner in 2 dimensions and Alberti, Baldo, and Orlandi. So this is 2010 and 2009, something like this, in which they show that the energy, again, when you subtract the divergent term and the core energy, they are able to show that this gamma converges indeed to the renormalized energy. Okay, another nice result related to Okay, so again, I had mentioned briefly. So this can be this whole framework, let's say, was helpful in the studies of true superconductors with magnetic field. The magnetic field is going to affect the location of the vortex. We have to include this magnetic potential in the model. And once you have a magnetic field, you don't need to impose this Dirichlet boundary condition. It's the magnetic field which is going to encourage, if you want, the vortex to enter. And so this is very also helpful in the superconductors. And let me try a different chalk here. In superconductors, so now it's the magnetic field. There's no boundary, no Dirichlet boundary condition. It is the magnetic field. Which gives some benefits. In the energy, for the vortex to compensate for the cost. Okay, so there has been lots and lots of studies by Sandier and Serfati on, well, what to do once you apply a magnetic field. What happens to the location of the vortex, they were able to study, for example, the first critical field at which, when you have an applied field, they do find that at order log epsilon, you will see vortices start entering the system, the material. They also studied, so there's lots and lots of study in the application where you apply, when you include the the magnetic field. But as I said, I am going to concentrate on the two component. So the other direction I'm going, no magnetic field, but the two component. So two component Ginsberg-Landau system. Okay, so again, in this case, my order parameter is C2 value, so it has two components, and the potential. Has a spin term. Okay, so again, the sigma value, so the potential in which this vanishes is the torus. The manifold in which vanishes is the torus. I'm going to again impose Dirichlet boundary condition. So I'm going to impose that you are sigma valued. So again, on this two torus. And I want that the degree of G be non-zero to get some vortices appearing. Okay, so same type, using similar methods as in the book of, as in the results of Bétuel, Brézé-Célin, we can show that psi epsilon converges to a limit, psi star, in Ck, except, of course, at the vortex. Is actually for every k we get convergence, for every k away from the vortices. And what is the cost? What happened to the cost of a vortex? Okay, so we do exactly the same type of idea. Now we have two components. So we're looking at the gradient of psi star, which is the sum of the component of psi star. And now you notice there's a little difference. Again, this was psi minus. The sigma here was psi plus squared is equal to a half is equal to psi minus square. So really you have modulus 1 over root 2. So when I try to associate the gradient of psi star with the gradient of the phase, there's going to be an extra 1/2. So in the energy cost, you're going to have pi over 2 times the degree of the psi plus component plus the degree of the C minus component. So again, the square of each times the log. So doing exactly the same calculation as I did. Okay? So this was again in the annulus around the vortex. Okay? So we see that this is going to be optimized. So before it was, we had just one phase, the degree for a minimizer wanted to be 1. Now it's going to be optimized if the degree of psi plus is 1 and the degree of psi minus is 0, or vice versa. Right? So this is optimized. When m plus is 1 and minus is 0, or n plus is 0. So these corresponds to different, hopefully, different topological type vortices due to the fact that we are in a system. And by the way, this corresponds to the fractional, if you go back using the change of variable in the spin model, those are the fractional degree vortices in this model. If you just go back to this. So these corresponds, this is 1/2, 1/2, and this is 1/2 minus 1/2. They correspond to the fractional degree vortices in the spin model. So we're going to have this topological type 1001. And notice here that if I took both components, psi plus, to be equal to psi minus, so both are the same, right? So both are the same. We are back to basically Ginsberg-Landau. So if I take psi plus to be psi minus to be 1/√2, I'll call this U Ginsberg-Landau, or classical. So if I choose psi, in other words, to be 2 copies of this in each component, then you observe that if you look at the Euler-Lagrange equation, it just solves the usual Euler-Lagrange equation. GL squared. Okay, so we conclude, so this is the classical Euler-Lagrange equation. So we conclude here that this 2-component Ginsberg-Landau does include the classical Ginsberg-Landau. What we are, of course, hoping is that we get something new happening because we have more type of topological vortices. And so what is the classical? I have just a few more minutes. The classical Ginsberg-Landau vortex would correspond to, since both components are Ginsberg-Landau, that would correspond to having degree 1 and 1. So the classical, and that's what I will call from now on, the classical Ginsberg-Landau vortex has n plus equal 1 equal n minus. It's just the classical. And so this corresponds to 2 vortex of degree 1, 0 and 0, 1 superimposed, in fact. And if you look at the leading energy, to have 2 fractional degrees or 1 classical Ginsberg-Landau gives you exactly the same contribution in energy. So, as I said, few minutes I have left. We do the same. We're trying to figure out what would be the location of the vortex. So we look at the renormalized energy, following again the method of Bétuel-Brézé-Sénin. We can do again using the harmonic conjugate to psi plus and psi minus. We end up with, so typically, suppose I'm imposing a degree let's say 3 and 2. So I would have here some degree, let's call this P1, P2, P3. Those would correspond, I'll call them plus to distinguish. This would be the degree 1, 0. The same topological type vortices will have, as before, log repulsion. But the other topological type, let me call it P2 minus, will not interact with, so they will have topological, again, repulsion with each other, but not with a different type. But you could have them, however, coincide. So if you look at the degree of psi star around what I have here, P1, which is the same if they are located at the same place, then this is a vortex 1, 1, both the 1, 0 and the 0, 1. So if you look at the degree, you will get a 1, 1 degree, the classical Ginsberg-Landau, while the degree, for example, around P3 plus, for example, would be 1, 0. So we can do our normalized energy. We find that, again, there is a log repulsion between similar vortices, but not between opposite vortices, so they can get close to each other. This is when you get the classical Ginsberg-Landau. They may not know. They may not. This is, again, this is in the limit, right? This is epsilon equals 0. So there's a small little subtlety, which is that I had described the core energy. It turns out that for epsilon small, positive, there is a difference in the core energy between the 1,1 vortices and the 1,0 and 0,1 vortices. And so this is where it will be, that's why we kind of need to figure out what the structure of the vortex look like. So we're going to do in my next lecture a blow up around these vortex to see what do these fractional, these degree vortices 1, 1, 1, 0, and 0, 1 look like, to see if we have any new type of behavior due to the fact that we are looking at a system and therefore different topological type of vortices. So I'll stop here.
Any questions, comments?